Gravity is one of the most fundamental forces in the universe, a force that shapes everything from the tiniest particles to the largest galaxies. It's a force that we all experience every day, yet its true nature is both fascinating and complex. To understand gravity is to delve into the very fabric of space and time, to explore the mysteries of how objects move and interact, and to appreciate the role this invisible force plays in the cosmos. Imagine standing on a mountaintop, looking out at the vast expanse of the earth below. You feel the pull of gravity anchoring you to the ground, a force that keeps you from floating away into the sky. This force, which seems so ordinary and familiar, is actually one of the most profound forces in the universe. It's the reason why the planets orbit the sun, why the moon orbits the earth, and why we experience the sensation of weight. The story of gravity begins with a simple observation: objects fall to the ground when released. For centuries, this observation was taken for granted, a part of everyday life that required no explanation. But in the 17th century, a brilliant scientist named Isaac Newton began to question why objects fall, and in doing so, he changed our understanding of the world forever. According to legend, Newton's curiosity about gravity was sparked by a falling apple. As he watched the apple drop from a tree, he wondered why it fell straight down to the ground instead of floating off in another direction. This simple question led Newton to develop the law of universal gravitation, a mathematical description of the force that causes objects to attract each other. Newton's law of universal gravitation states that every object in the universe attracts every other object with a force that is proportional to their masses and inversely proportional to the square of the distance between them. In other words, the force of gravity between two objects increases with their mass and decreases as they move farther apart. This law was revolutionary because it applied not only to objects on Earth but also to celestial bodies like the moon, planets, and stars. Newton showed that the same force that causes an apple to fall to the ground also governs the motion of the planets around the sun. This realization was a major breakthrough in science. Before Newton, the motions of the planets were explained by complex systems of epicycles and deferents, which attempted to account for the observed movements of celestial bodies. Newton's law of universal gravitation provided a simple and elegant explanation for these motions, unifying the physics of the heavens and the earth under a single theory. With Newton's law of gravity, scientists could now predict the motions of planets, moons, and comets with great accuracy. It was a powerful tool that allowed humanity to understand the mechanics of the solar system and laid the groundwork for the development of modern physics. But as successful as Newton's theory was, it was not the final word on gravity. Over time, new observations and experiments would reveal the limitations of Newton's law and lead to a deeper understanding of this mysterious force. In the early 20th century, a new theory of gravity emerged that would revolutionize our understanding of the universe once again. This theory, known as general relativity, was developed by the German physicist Albert Einstein. General relativity provided a new way of thinking about gravity, one that was radically different from Newton's view. Einstein's theory of general relativity is based on the idea that gravity is not just a force between objects but a curvature of space and time itself. According to general relativity, massive objects like the Earth or the Sun cause the fabric of spacetime to curve, and this curvature affects the motion of other objects. In other words, gravity is the result of objects moving along curved paths in spacetime, rather than being pulled by a force as Newton had described. One of the most famous analogies used to explain general relativity is the rubber sheet analogy. Imagine a large, flexible sheet stretched out horizontally. If you place a heavy ball in the center of the sheet, it will cause the sheet to sag and create a depression around the ball. Now, if you roll a smaller ball across the sheet, it will move along a curved path as it approaches the depression. The heavier the ball in the center, the greater the curvature of the sheet and the more the smaller ball's path will be bent. In this analogy, the sheet represents spacetime, the heavy ball represents a massive object like a planet or star, and the smaller ball represents another object moving through space. The curvature of the sheet is analogous to the curvature of spacetime caused by the presence of mass, and the curved path of the smaller ball represents the effect of gravity on the motion of objects. General relativity was a revolutionary idea because it fundamentally changed our understanding of gravity. It showed that gravity is not a force that acts at a distance, as Newton had described, but rather a manifestation of the geometry of space and time. This new perspective on gravity had profound implications for our understanding of the universe. One of the most striking predictions of general relativity is the existence of black holes, regions of space where gravity is so strong that not even light can escape. Black holes are formed when massive stars collapse under their own gravity, compressing their mass into a single point known as a singularity. The gravitational pull of a black hole is so intense that it warps spacetime to an extreme degree, creating a hole in the fabric of the universe. The concept of black holes was once purely theoretical, but today we have strong evidence that they exist. In 2019, the first ever image of a black hole was captured by the Event Horizon Telescope, providing direct visual confirmation of these enigmatic objects. This image showed the shadow of a black hole in the center of the galaxy M87, surrounded by a glowing ring of hot gas. It was a momentous achievement in astronomy and a powerful confirmation of Einstein's theory of general relativity. General relativity has also been crucial in understanding other cosmic phenomena, such as gravitational waves. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as the collision of two black holes. These waves travel through the universe at the speed of light, carrying information about the events that produced them. The existence of gravitational waves was predicted by Einstein's theory, but it wasn't until 2015 that they were directly detected by the Laser Interferometer Gravitational Wave Observatory, LIGO. This discovery opened up a new way of observing the universe, allowing scientists to study cosmic events that were previously hidden from view. Despite the successes of general relativity, gravity remains one of the most mysterious forces in the universe. There are still many unanswered questions about gravity, particularly when it comes to understanding how it works on the smallest scales. Quantum mechanics, the theory that describes the behavior of particles at the atomic and subatomic levels, does not yet fully explain gravity. This has led to a major challenge in modern physics, the quest for a theory of quantum gravity that can reconcile general relativity with quantum mechanics. One of the leading candidates for a theory of quantum gravity is string theory. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings of energy. These strings can vibrate at different frequencies, giving rise to different particles. In string theory, gravity is mediated by a particle called the graviton, which is a quantum of the gravitational field. While string theory has not yet been experimentally confirmed, it offers a promising framework for understanding gravity at the quantum level. Another area of active research is the study of dark matter and dark energy, two mysterious components of the universe that are believed to make up most of its mass and energy. Dark matter is thought to be a form of matter that does not interact with light, making it invisible to telescopes. However, its presence can be inferred from its gravitational effects on visible matter, such as the rotation of galaxies. Dark energy, on the other hand, is believed to be responsible for the accelerated expansion of the universe. Both dark matter and dark energy challenge our understanding of gravity and suggest that there may be new physics waiting to be discovered. Gravity is not just a force that governs the motion of planets and stars, it also plays a crucial role in the formation and evolution of the universe itself. The Big Bang, the event that marked the beginning of the universe, set in motion the expansion of spacetime. Gravity acted as a counterbalance to this expansion, pulling matter together to form galaxies, stars, and planets. Over billions of years, gravity has shaped the large-scale structure of the universe, creating the vast cosmic web of galaxies that we observe today. On a smaller scale, gravity is responsible for the formation of planetary systems. When a cloud of gas and dust collapses under its own gravity, it can form a star and a surrounding disk of material. This disk eventually coalesces into planets, moons, and other objects, creating a solar system. Gravity continues to play a role in the dynamics of these systems, governing the orbits of planets, moons, and asteroids. In our own solar system, gravity is the force that keeps the planets in orbit around the Sun. The Sun's immense mass creates a strong gravitational pull that keeps the planets from drifting off into space. Each planet follows a curved path around the Sun, known as an orbit, and the shape and size of these orbits are determined by the balance between the gravitational pull of the Sun and the planet's own velocity. The same principle applies to the Earth-Moon system. The Moon is held in orbit around the Earth by gravity, and the gravitational interaction between the Earth and the Moon is responsible for the tides. The gravitational pull of the Moon causes the Earth's oceans to bulge, creating high and low tides. This tidal interaction also gradually slows the Earth's rotation and causes the Moon to slowly move away from the Earth over time. Gravity also plays a role in the lives of stars. Stars are born from the gravitational collapse of gas clouds, and gravity continues to shape their evolution throughout their lifetimes. In the cores of stars, gravity creates the high pressures and temperatures needed for nuclear fusion, the process that powers stars. As stars exhaust their nuclear fuel, gravity causes them to collapse, leading to the formation of white dwarfs, neutron stars, or black holes, depending on the mass of the star. The study of gravity has also led to practical applications here on Earth. One of the most important of these is the development of the Global Positioning System, GPS. GPS relies on a network of satellites that orbit the Earth, and their positions and movements are influenced by gravity. To provide accurate location information, the system must account for the effects of gravity on the satellites, as well as the curvature of spacetime described by general relativity. Without these corrections, GPS would not be nearly as accurate as it is today. Gravity also affects our everyday lives in ways that we may not always notice. For example, gravity influences the flow of water in rivers and oceans, the movement of air in the atmosphere, and even the structure of our bodies. Our bones and muscles are adapted to withstand the constant pull of gravity, and long periods of weightlessness, such as those experienced by astronauts in space, can lead to muscle and bone loss. This is why astronauts must exercise regularly while in space to counteract the effects of reduced gravity. In the end, gravity is a force that connects us to the universe in profound ways. It shapes the cosmos, governs the motion of celestial bodies, and influences the very structure of space and time. Yet, despite its importance, gravity remains one of the most mysterious and least understood forces in nature. As we continue to explore the universe and push the boundaries of our knowledge, we may uncover new insights into the nature of gravity and its role in the cosmos. Understanding gravity is not just a scientific pursuit, it is also a journey of discovery that reveals the interconnectedness of all things. From the falling apple that inspired Newton to the black holes and gravitational waves that challenge our understanding today, gravity is a force that invites us to explore the universe and our place within it. It is a force that reminds us of the beauty and complexity of the world around us, and of the endless possibilities that await those who seek to understand it.